Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about some questions from the question bank from the Module 2. So here the Module 2 is about the basic electrical laws. So in the Module 2, we have discussed the Ohm's law and also the basic techniques that are using to find the current flowing through the element or the voltage across any element. So in this module, we have already discussed the basic network reduction techniques, which are loop analysis, nodal analysis, and also here we have discussed how to, discussed find the equivalent resistance between the two terminals. And in that case, we have also discussed star to delta and delta to star connection. So these are the topics, the various topics that we have covered in the module 2. So based on these topics, so we are going to discuss some questions from the question bank. Then first of all, let me start with the equivalent resistance between the two terminals. So in this given problem, we need to find the equivalent resistance between the two terminals, which are A and B. So here it is A and B. So now here we need to identify what are the two resistors which are connected in series and what are the two resistors which are connected in parallel, so that we can replace the series combination or the parallel combination of the resistance with its equivalent resistance value. So as we know, if the two resistors are connected in series, then the equivalent resistance is equal to the sum of the two resistance values. So which means, let us consider here R1 and R2 are connected in series, then the equivalent resistance between the two resistors here it is R1 plus R2. And similarly, if R1 and R2 are connected in parallel, then the equivalent resistance between these two resistors here it is, of course, one way here it is 1 by R equivalent, which is equal to 1 by R1 plus 1 by R2. Or in another word, simply R1 R2 by R1 plus R2. Then here another key point is how to identify whether the two resistors are connected in series or parallel. So here, if the two resistors having one common point and that common point does not share with any other element, then we can say those two resistors are connected in series. So which means here, let me start from the right hand side. So here the 2 ohms and 2 ohms. So let us see whether these 2 ohms and 2 ohms are connected in series or parallel. So here don't think like if the two resistors are connected in opposite way, okay, then these two are in parallel and side by side and series. So it is not like that. So if the two resistors having only one common point or one common node and that node does not share with any other element, then we can say those two resistors are in series. So let us consider here the 2 ohms and 2 ohms. So here these 2 ohms and 2 ohms having only one node, let us consider here, of course these two are represents the same node, because in these 2 points there is no element connected, so that's why these 2 nodes represents the same node. So here 1 and 1. Of course here these 2 resistors having only common node, that is 1, and this common node does not share with any other element, right? Because here this node is connected to only these 2 ohms and 2 ohms. There is no other third element connected to this common node. Then we can say here the 2 ohms and 2 ohms are connected in series. Then if the 2 ohms and 2 ohms are connected in series, then what is the equivalent resistance? So here 2 plus 2, which is equal to 4, right? Then you can just simplify this, redraw, okay, by replacing this with this. So here let me redraw. And another thing here, is there any other possibility? Of course here the 2 ohm, okay, we will come later, then one by one. So here the other resistors here, the 2 ohms, and here 3 ohms is there, and again here 2 ohms is there, Then here the 2 ohms is there. Again here 4 ohms is there. Then here we are replacing this 2 and 2 with the equivalent resistance, which is 2 plus 2, 4 ohms. This is 4 ohms resistor and here it is 4 ohms resistor. So this one we are replacing with this 4 ohms resistor, right? So again here the remaining resistors are as it is, 2 ohms, 2 ohms, 2 ohms and 4 ohms, right? Now, as you can see here, of course here 4 and 4 ohms having how many common nodes here? 2 common nodes are there, okay? So because these 2 nodes represent same, 1 and 1, and this is also represent same, so 2 and 2. So these 2 resistors having 2 common nodes, okay, and the 2 common nodes are connected to the common nodes are shared with other element also. But in case of parallel, then how to identify the parallel? If the 2 elements are having 2 common nodes, okay, then we can say those 2 are having parallel. Those 2 are connected in parallel. Of course, it may or may not share that node with other element. Here it is not a criteria. So only the criteria is whether the 2 resistors having 2 common nodes or not. If the 2 resistors having 2 common nodes, then we can say those 2 resistors are connected in parallel. So in case of, then here the 4 ohms and 4 ohms are having the 2 common nodes. So which means here these 4 ohms are connected in parallel. Then we can replace these 2 resistors with an equivalent resistance. So according to this formula, so here 4 into 4 by 4 plus 4. So here 16 by 8, then here it is 2 ohms. Then the equivalent resistance here it is 2 ohms. Then you just replace this one with the 2 ohms. Then I am just replacing this one with the 2 ohms, right? So here this is 2 ohms, right? Then now again see here these 2 ohms and 2 ohms are connected in series or parallel. Okay, so first let's check how many common nodes are there in between these 2 resistors. Only one common node, this one. And this common node does not share with any other element. Of course, here this common node is connected to only these 2 and 2. There is no other element connected to that common node. Then we can say these 2 are in series. So again here 2 plus 2 is equal to 4. Then I am just replacing this one. So by replacing, and here it is 4 ohms, right? Then again, as you can see here, these 2 resistors having these 2 and these 2 ohms resistors having 2 common nodes, okay. So that's why these 2 are in parallel. So the equivalent resistance here it is 2 into 2 by 2 plus 2, okay. So here it is 1 ohm. Then we can replace this with 1 ohm. Here it is 1 ohm. Then again here these 3 ohms and 1 ohm are having only one common node, and this common node does not share with any other element. Then we can say these 3 ohm and 1 ohm are in series. So 3 plus 1, 4. Then I am just replacing this one with the 4 ohms, the equivalent resistance where it is 4 ohms. So again here these A and B terminals are remain same. Then now 4 and 4 ohms are having 2 common nodes. So which means here 4 and 4 are in parallel. Then again here 4 into 4 by 4 plus 4. Then here it is, just now we have seen 2 ohms. So then we can replace this with 2 ohms. So here then the equivalent resistance between the A and B terminal, here it is 2 ohms. So here RAB, which is equal to 2 ohms. So this is the answer for the given question. So like this you can find the equivalent resistance between any 2 terminals for any given network. So here the 2 points that we should remember, one is how to identify the series combination and how to identify the parallel combination. So the series combination means if the 2 resistors having only one common node and the common node does not share with any other element, then we can say those 2 resistors are connected in series. As we know already the properties, okay, so the current flowing through the series element is same. Then coming to the parallel, If the two elements are having the two common nodes, then we can say those two are connected in parallel. Then let us see this, another example. So find the equivalent resistance between the A and B terminals again. So anyway, here these are the A and B. So, and another thing, we should not disturb the A and B terminals anyway. Okay, that means the node A and node B, because we are going to find the equivalent resistance between these two nodes, right? Then here, let us start from here. Again here, as you can see, these 2 ohms and this 10 ohms are connected in series or parallel. Okay, so let me check how many common nodes are there in between two nodes. Okay, only one common node, and the common node is not shared with any other elements. So we can say these two are in series. So here the 10 plus 2 is 12, right? Okay, then let me draw here this one again, redraw. So in every step we have to draw in your examinations. Okay, I mean in your theory examinations you should draw step by step. Okay, then this resistor, and here it is one, and then yeah, this one and this one, right? Then now we are going to replace these two resistors with a equivalent resistor. So let me draw here this one. So here 10 plus 2, here it is 12 ohms, and here it is 6 ohms, again here it is 6 ohms, and again here it is 6, and then here it is 4, here it is 8, and here it is 4, right? So then here it is again 8, and here it is 6. So we have to find the equivalent resistance between these two terminals A, B, right? So now you can see these 12 ohms resistor and this 6 ohms resistor, okay, are connected in parallel, because this is one common node, right? This is one common node, and this is another common node too. So these 12 ohms and 6 ohms are connected in between these two. So we can say these two are again parallel. Okay, then parallel means here 6 into 12 by 6 plus 12. So here it is 4 ohms, right? Then now we can replace this one, this and this one with 4 ohms, right? So again, as you can see here, these 4 ohms and 6 ohms are in series, because here having only one common node. Then you can replace this with a 6 plus 4, 10. Then here this will become 10, right? So now just 10 and 6 again are in parallel, because these two are having two common nodes. Okay, then in this case here it is 10 into 6 by, so 10 plus 6, so here it is 60 by 16. So here it is 3.75 ohms. Then similarly here these two again, yeah, this is 3.75, and again these 3.75 and 4 ohms are in series. Okay, then you can replace, here it is 7.75, 3 plus 4, so 7.75. Again here the 7.75 and 8 are in parallel, because these two are having two common nodes. Okay, then you can replace this, and again here, so like this you can convert. Okay, so here 8 into, I mean 8 and 7.75, then we can see here, then here this 8 into 7.75 by 8 plus 7.75, so which is equal to here 3.93. Okay, then replace this one. Here it is, just I am going to replace this. Here it is as it is. Okay, so this one can be replaced with 3.93. Okay, in other words, we can make it as a 4, right? So here let me just make it a round figure as a 4. Then again these 4 and 4 are having only one common node, so we can say these 4 and 4 are connected in series. Then this one we can replace with an equivalent resistance. 4 plus 4 is equal to 8. Then here it is 8 ohms. Then these 8 and 8 are having two common nodes. This is one and this is the second common node. So 8 and 8, so 8 into 8 by 8 plus 8, then you can say here it is 4 ohms, right? Then this can be replaced with 4 ohms. So this is 4 ohms. Then again here 6 and 4 having only one common node, so we can say these two are connected in series. Then here the equivalent resistance here it is RAB, which is equal to 6 plus 4, which is equal to 10 ohms. So this is now your answer. So this is the way to simplify or to reduce the network or to find the equivalent resistance across any two terminals. Now coming to the another topic, which is mesh analysis, or we can also call it as a loop analysis, right? So here apply the mesh analysis and calculate the current flowing through the 3 ohms resistor. Of course, here don't get confused. Here there are 2 3 ohms resistors are there. Then we should find the current flowing through each 3 ohms resistor, right? So here there are two ways to find the mesh analysis. I mean to apply the mesh analysis. Here, as you can see, there is a concept of super mesh analysis also there, right? So when we can apply the super mesh analysis, okay, so if there is a current source between the two loops, then we can apply the super mesh analysis, right? Or in another words, here we can convert this current source into the voltage source, then after that, so that we can make it these 3 loops as a 2 loops, and then we can apply the mesh analysis. In the both the way you can do. Okay, so first let us, because anyway super mesh analysis we will discuss later, but now let me go with by converting this current source into the voltage source, because this source transformation that we have already discussed in the previous class. So the same concept here I am going to apply. Then in this case, this current source, okay, so that I am going to convert into the voltage source. Then V is equal to I into R. Okay, then here I is 8 and R is 3. So then here it is 24 volts. V is equal to 24 volts with a resistance of 3 ohms. Then this network will become, here it is again the plus and minus. So here it is 12 volts. Then this 6 ohms as it is, and here it is 6 ohms again as it is. Then again here this 3 ohms is as it is. But here this the current source that we are transformed into the voltage source, then here you will be having the resistance again here the 3 ohms, okay, and here it is, then this is the voltage source. Okay, let us consider here it is V1 and here it is V2. So here V2 is 24 volts, and again here these 3 ohms is as it is, again here these 3 ohms is as it is. So now we are going to find the current flowing through these 3 ohms. What is that? The current flowing through these 3 ohms that we need to find. Of course, here then this is again 6 ohms and here it is again 6 ohms. Now let us apply the mesh analysis. Okay, so here it is plus minus and here it is plus minus. Then in this way, here it is plus minus and here it is plus minus and here it is plus minus. Then the loop 1 direction is, let us consider here it is like this. So let us consider the current is I1, and here the loop 2 direction is, let us consider here it is I2. So you are having 2 loops. So that let me write, of course, for the mesh analysis, we have to apply the KVL. As we know, the algebraic sum of the voltage across each, the algebraic sum of the voltage is equal to, across each element is equal to, in a loop, sorry, the algebraic sum of the voltage across each element in a loop is equal to 0. Then here, we can write this equation as a, let me start with 6. So here 6 into I1 plus, again 6 into, because here the current flowing through the 6 ohms resistor with respect to loop 1 is I1, with respect to loop 2 is I2, which means in the 6 ohms the current will, the I1 and I2 both currents will flow, but both are in opposite direction. Not opposite, so sorry, here it is in the same direction, because with respect to I1 also in this direction, and with respect to I2 also, here it is flowing in this direction, right? Then here 6 into I1 plus I2, okay, so which is equal to 12. Let us consider this is equation number 1. Then similarly with respect to loop 2 here, okay, let me start with here 3. So 3 into I2, again plus 3 into I2, okay, because with respect to this, and plus here 6 into again I1 plus I2, okay, which is equal to here 24. This is equation number 2. So then by solving these two equations, okay, so by simplifying, let us just simplify. Here it is 12 I1 plus 6 I2, which is equal to 12. So we can furthermore simplify this 6 ones and 6 2 and 2. So here it is 2 I1 plus I2, which is equal to 12. Then similarly here, which is, let us consider here it is again equation A. Then if you simplify this, here it is 336 I2, okay, plus 6 I1 plus again 6 I2, which is equal to 24. The same way here it is again 6 I1 plus 12 I2, which is equal to 24. Then same way here 6 1, 6 2, 6 4s, right? Then this equation will become here I1 plus 2 I2, which is equal to 24. Then by solving this equation A and B, then you can find the I1 and I2 values. Then here the current flowing through these 3 ohms, okay, either these 3 ohms and these 3 ohms is same, which is the current I2. Whatever the value that we will get for the I2, so that amount of the current will flowing through this 3 ohms resistor. Because here 3 ohms, these 3 and 3 are connected in series, then as we know the current flowing through the series elements is same. Then here, of course, this is also a problem to find the equivalent resistance between the terminals B and C. So here we need to find the equivalent resistance between these two terminals, right? So here, let us see, okay, let us consider here these two, this resistor and this resistor. As you can see, these two resistors having, okay, one common node, but this common node is connected to again this 4 ohms resistor. So which means here these two are not in series, even though not in parallel, because these two don't have two common nodes, right? So like this here, if you can check the combination of all resistance, okay, so here you can't find whether, you can't find any two combination of the resistors are connected in series or parallel. Okay, so neither in series nor in parallel. Then in that case, how to reduce the network? So in that case, as we discussed already, so star to delta and delta to star connection, right? So which means here, this delta connection is there. So this delta connection that we can transform into star, then we can able to simplify this, right? Then how to convert this delta into the star, that we are going to discuss here. Then this way you can convert, because let us consider here again star network I am drawing here in between the delta, right? So let us consider here it is R1 and here it is R2 and this is R3. Let us consider, right? Then here R1, which is equal, what are the two resistors which is connected to the same node which R1 is connecting? So 6 ohms and 6 ohms. So 6 into 6 by the total resistance here it is 6 plus 6 plus 6. Similarly here R2 also, of course all are 6. Then R2, the other two resistors connected to that particular node are 6 into 6 by 6 plus 6 plus 6. Then similarly here R3 also, because all the resistors having the same value, so it is easy for us to find the value. Okay, so here 36 by, okay, so 6 plus 6, 12 plus 18. So here 18 and 2. So here it is 2 ohms. The similar way here also it is 2 ohms and here also it is 2 ohms. Or in another words, in a delta connection, if all the resistors having the same resistance value, then we can easily convert the star value, which is R by 3. Okay, so which means here it is 6 by 3, so which is 2. So all the resistors which are presented in the star network are having the same value, which is 2. Right? So now let me draw the equivalent resistance now, the equivalent circuit after converting the delta into the star. So which means here this is the star, right? So anyway here this is 2 ohms, again one more resistor is there 2 ohms, and this is 2 ohms and one more resistor is there with 2 ohms, and here it is, this is 2 ohms and another resistor is there with 2 ohms, right? So again in between the 4 ohms resistors are there. So 4 ohms resistor, and this is also one more 4 ohms resistor. So here it is 2 ohms and 2 ohms. So 2 ohms, 2 ohms, 2, 2, and this is 4, 4, and 4. Right. So now here again you can see here these 2 and 2 are in series because having only one common node and the common node is not shared with any other element. The similar way this and this, then now this circuit will become, anyway here again the 3 nodes are there A, B, C, then we are going to, and we have to find the resistance, equal resistance between B and C. So here the as it is the 4 ohms are there, so we did not disturb these 4 ohms resistors. Then here also 4 ohms resistor is there, so 4 ohms and 4 ohms. So and in between there is a star, in between there is a star, right? So here this star network also having the same 4 ohms and 4 ohms and 4 ohms, right? So now let us see again, is there any series and parallel combinations? Of course, as you can see here, again there is no series and parallel combinations here, because as you can see here, these 3 having, these 2 having one common node, but the common node is connected to again 4 ohms. So which means now again we are going to convert this star into the delta, because sometimes one time conversion is not enough, so we need to convert again. So again here we are going to convert this star into the delta. So if you are converting the star into the delta, so which means here, let me draw. So here the star network between this delta, here it is like this, right? So now let us consider here again it is RA, RB, and RC. Okay, so in this case, so suppose if you want to find RA, so RA is equal to, what are the, what is that RA? So these 2 resistors are connected, right? 4 and 4. So here 4 plus 4 plus 4 into 4 by 4. So let me show you how this will get. Yeah, this way. Okay, so if you simplify this, then you will get the same way, because here if you want to find RA, so R1 R2 by R1 into R2. Okay, yeah, here it is R1. Okay, if you want to find R1, okay, delta to star, okay, R1 is equal to RA RB by RA plus RB plus RC. So the other way here it is delta to star, that we can convert here it is. Okay, so which means, let me write here itself. So suppose if you want to find RA, okay, and RB and RC, because now the star is there, now we are going to convert the star into the delta. So here RA, here it is R1 plus R2 plus R1 R2 by R3. Then similarly RB is equal to, where is RB? Here RB is in between R1 and R3. So R1 plus R3 plus here R1 R3 by R2. Then similarly here RC is in between R2 and R3. So R2 plus R3 plus R2 R3 by R1. So this way we can convert the star into delta, right? So the same way here you can substitute. Okay, so which means here it is 4 plus 4, 8 plus here 4 into 4, 8. Okay, and 8 by 4, here it is 2. So here it is 10. right? The same way other RB is also you will get the same value, and RC is also you will get the same value, right? So after that you can easily, it is easy to find because these two are again connected in parallel, and these two are connected in parallel, and these two are connected in parallel. Okay, and then these two again connected in series, and the combination is parallel with the BC. Then you can find the equivalent resistance between these two. The nodal analysis, okay, the same way that we have discussed in the previous case. Okay, so we can simply apply the nodal analysis. But here one more thing that we should understand here it is, okay, super node analysis, right? In the previous case we have discussed the super mesh analysis. So here we are going to discuss about the super node analysis. If, because here there is a voltage source between the two nodes, if there is a voltage source between the two nodes, right, then we can go for the super node analysis. Then by using that super node analysis, we can easily find the node voltages, which means the node voltage across, the node voltage at point A and the node voltage at point B. So that we can find. Then here, another one, calculate the voltage to be applied across the AB in order to drive current of 5 amperes in the circuit, right? So here, of course, this is also the same way, like we need to find the equivalent resistance between the A and B terminals, because as they are seen, so what is the voltage that we must apply across the A and B terminals to deliver a current of 5 amperes. So which means here, as we know, V is equal to I into R. So I, they have given 5 amperes. So if you are able to find the total resistance R across the A and B terminals, then it is easy to find the voltage V across the A and B terminals. That is what here we need to find. So the same way that we have followed before. Okay, so first of all we should find the equivalent resistance, so that we should see, okay, what are the two combinations are connected in series or parallel. Okay, so if the two combinations are connected in series, then R1 plus R2, and connected in parallel, then R1 R2 by R1 plus R2. So here, as you can see, here also it is not possible to convert without using the star to delta and delta to star transformation. Here it is very difficult to find the equivalent resistance between the two terminals. So here, for that, I am just converting here, two deltas are there. So two deltas that at a time that I am going to convert into the star, right? So which means here, let me convert this one into the star and this one into the star. So again here also this is, and this is one more resistor, and this is another one resistor. Okay, so this star I am going to convert into the delta. Oh, sorry, this delta, these two deltas are that I am going to convert into the star. So again, same way here, let us consider here it is R1, R2 and R3. Okay, the same way here also, R1, R2 and R3, right? So the same way here, that as we have discussed in the previous case. Okay, so the same way here we can discuss. Here it is RA RB by RA plus RB plus RC. Okay, so the same way here also we can write. Fine. So in this case, then again, what is this here? RA RB. So which means, suppose if you want to convert R1, then 2 into 3 by 2 plus 3 plus 5. Then similarly here, suppose if you want to find R1 R2, here it is 2 into 5 by, so 2 plus 3 plus 5. And then similarly here, 3 into 5 by 2 plus 3 plus 5. Then the same way, the second one also, here suppose if you want to find R1, then 5 into 10 by, here 5 plus 10 plus 10. Then similarly here, if you want to find R2, then again 5 into 10 by, same 5 plus 10 plus 10. And here R3 is equal to, again here it is 10 into 10 by 5 plus 10 plus 10. So by solving this, we can find the R1, R2, R3 values in the both the cases. Okay, in the first delta 2 star and the second delta 2 star. Then after that, it is very easy to find the equivalent resistance between the terminals A and B. So after finding the equivalent resistance between the A and B, then you can use simply V is equal to I into R equivalent. So as we know already, I value that they have given as a 5 amperes, then substitute the R equivalent value, then you can find the total voltage field. This is how we can find the voltage across these two terminals. Okay, because here the simplification I am not going to explain, because here by using a calculus, just you can simplify and find the R1, R2, R3 values. So this is how these are the various problems that are present in the question bank. Of course, there are some other problems are also there, but those problems are also similar to these problems. Okay, so one is mesh analysis and super mesh, and again nodal and super node analysis. And you can see there is an exclusive video, okay, for the super mesh analysis and as well as the super node analysis. Okay, so that you can go through, so that you can able to solve the problems which are presented in the question bank. So here I have just took some sample questions from the question bank. Okay, but I didn't cover all the problems from the question bank, but you can just go through the question bank so that you will get understand, because the same concepts, okay, which we have already discussed, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.